Hey everyone, this video is going to cover the first two objectives for 6.4, where we're going to be looking at some properties of functions. So specifically, we're going to look at the domain and range of each of these six trig functions, as well as determining their periods. Okay, so for your trig functions, you have to understand that the input or the domain of your trig function represents an angle measure. Okay, and then the output represents the value of the ratio that defines the trig function, okay? So when you're determining the domain for each of these, you have to ask yourself, are there any angle measures that wouldn't yield a specific value for the trig ratio that defines it, okay? And if that's the case, they're going to happen at some of the quadrantal angles, okay? So let's start with the sine function, all right? Now sine we know to be y over r, okay? So we're taking the y coordinate of the point that's defining our angle divided by the r value, okay? And it doesn't matter what point's defining the angle, you're always going to get a ratio for y over r, okay? There's always going to be a value that results from that. So I'm going to say that the domain for this is all real numbers, okay? Or I'll use both notations, right? It's going to be the same for cosine. Cosine's defined to be x over r. Doesn't matter what point's defining your angle, you'll always have an x coordinate, you'll always have an r value associated with it. Okay. All right, now tangent is the first function that we'll say doesn't have a domain of all real numbers. Tangent's defined to be y over x, okay? And what we want to focus on here is that the denominator of this fraction is x, and it is possible that x could sometimes be equal to 0, okay? So this is where the unit circle comes into play. Look at the first angle measure on that unit circle that's defined by a point whose x value is 0. That would be right here at pi over 2, right? The point that defines it is 0, 1, okay? So that means pi over 2 has to be excluded from the domain of the tangent function, okay? But that's not the only place where that's going to happen, all right? If you go down to 3 pi over 2, right here, you're going to end up with the same scenario, right? Y over x would be negative 1 over 0, which would be undefined, okay? And that's going to keep happening as you continue to rotate every pi radians or 180 degrees, okay? So that tells me there's an infinite amount of angles that have to be excluded from the domain of tangent, and they're all multiples of pi over 2 or 3 pi over 2, okay? So here's how I'm going to write this. I'm going to say that the domain for tangent would be any value of theta as long as it doesn't equal pi over 2 itself plus any multiple of pi, okay? So I'm saying pi over 2 plus pi k, where k represents an integer, okay? And all that really means is the first place where tangent would be undefined is at pi over 2. The second place would be at pi over 2 plus pi. The third would be at pi over 2 plus 2 pi, which would take you back to the same location. It would be coterminal to pi over 2. And you can, add on as many multiples of pi as you would like, okay? All right, now what about the cosecant function? Cosecant's defined to be r over y. All right, so now we're focusing in on, are there any angles that give you a y coordinate that's 0? And that would take place right here at 0 radians or 0 degrees, and then again right here at pi radians or 180 degrees. Okay, So the first place it happens at is 0. The next place it happens at is at pi, and then after that it would be at 2 pi, then 2 pi plus another pi, and so forth. So I'm going to write that. I'm going to say that theta cannot equal. You could write 0 plus, but it's not necessary. Really, you just have to say pi k, where k is an element of the integers. Okay. All right, now secant and cotangent, we're going to be able to reason these out very quickly. Secant's defined to be r over x, and we're in the same situation as we were for tangent in the fact that we have an x in our denominator. So that means secant is going to have the same domain as the tangent function. Okay. And similarly, cotangent is defined to be x over y, where we have y in the denominator. And this is going to be the same domain as it was for cosecant. All right. So there are your 6 different trig functions domains, and these are going to get reinforced when we start to graph each of these functions as well. Okay. Now let's talk about range. So range is, of course, your output, right, for a function. And for the trig functions, it represents the value of the trig ratio itself, okay? So what you need to ask yourself is when you compare the values of x, y, and r for each of the ratios that define these functions, are there any restrictions on what that output is going to be, okay? So for the sine function, it's defined to be y over r, okay? Now, r, from the triangular approach, r is like the length of the hypotenuse of the triangle, right? And we know that that is always going to be longer than the x value or the y value of the point that's associated with the angle itself, okay? Now, y and r, they can be equal to each other in the case of the quadranals. They could have the same value, but r will never be smaller than y, okay? So for this fraction of y over r, that's telling me that the denominator will never be smaller than the numerator, which means the value of the fraction itself for y over r is going to have to be somewhere between -1 and +1. Okay. It would be the same for the cosine function. Okay. Your x will never be larger than your r value. They could be the same though. So the result of x over r is going to have to be somewhere between -1 and +1. Okay. Now tangent is defined to be y over x. Okay. Sometimes the y value of the point defining the angle is larger than x. Sometimes it's smaller. Sometimes they're the same. Okay, that means you could have any possible result for this ratio of y over x. So the tangent function has a range of all real numbers. Okay, cosecant r over y. This is going to be the exact opposite as it was for the sine function, okay? Now it's the denominator that's always going to be smaller than the numerator, or maybe they could be the same size. So that means this is going to result in values that are between -1, well, from infinity to -1, as well as from 1 to infinity. Okay, so notice that's got the exact opposite range as what the sine function did. Okay, it's going to be the same for the secant function, r over x. Sometimes r and x will be the same, but other than that, x will be smaller than r. So since that's x is in the denominator, this is going to result in a value that's either smaller than -1 or larger than +1. Okay. And then the cotangent function is defined to be x over y. This is going to be the same as it was for the tangent function. X over y could result in any real number. Okay. All right, and once again, those ranges for each of these, they'll be reinforced as we start graphing these functions, okay? All right, now let's talk about the period of a trig function, okay? So since all the results of any trig function can be repeated with more than one unique measure, they're all said to be periodic. And the period of your function, it tells you how many degrees or how many radians it's going to take for the results of that function to turn out to be the same, okay? So the four functions that are over on the left-hand side, they all have a period of 2 pi, okay? Meaning you're not going to see your values completely repeat until you do a full rotation of 2 pi in either the positive or negative direction. So I'm going to say that the sine of the angle theta is equivalent to sine of my angle theta added with 2 pi k, where k, once again, is just an element of the integers. K represents an integer. Don't get confused by that notation. 2 pi k just means you're adding on a multiple of 2 pi. So 2 pi, 4 pi, 6 pi. It could be negative 2 pi, negative 4 pi, so forth. Okay. It would be the same for these other three below. So cosine also has a period of 2 pi. So does secant, and so does cosecant. Right? The only two functions that don't have a period of 2 pi are the tangent and cotangent functions. Instead, their period is pi. So you only have to go half of a rotation around before you start to get everything to repeat, okay? So tangent of theta would be equivalent to tangent of itself added with just pi k. Same thing with cotangent. All right. So let's see these properties at play here. All right. Knowing your periodic properties can help you in evaluating trig functions of larger or smaller angles. Okay. So sine of 390 degrees, I know that sine has a period of 360. Okay. So or 2 pi. So I could rethink of this as sine of 360 plus 30 degrees, okay, which really means this is just equivalent to sine of 30 degrees. And sine of 30 degrees is 1/2. You could reason that out off the unit circle, or you could just draw out special right triangle with a 30-degree angle here, 1, radical 3, 2. So notice your y value is 1, your r value is 2. Right? Tangent of 5 pi over 4. Well, I know that tangent has a period of pi, so I could rethink of this as tangent of pi, and pi plus what gives you 5 pi over 4? What would be pi over 4? So this means this is equivalent to tangent of just pi over 4, which is exactly 1. You can reason that out again off the unit circle, or draw out a 45-degree reference triangle, 1, 1, radical 2, tangents y over x, 1 over 1.